In this talk, I will present our research on snake robots. My area of expertise is autonomous robots, and the motivation for our research on snake robots comes from the mobility that we find in biological snakes. Mobility is an important feature for autonomous robots, and snakes, they can move in virtually any environment, including rough terrain where, for instance, wheeled or legged robots could run into problems. We here see how a biological snake moves in quite cluttered terrain, and instead of avoiding obstacles, it uses the obstacles, pushing against them to move even faster forward. Snakes are also very good climbers, and also here we can see how the snake uses irregularities in its environment to push itself forward. Snakes are also excellent swimmers, and due to their slender and flexible body, they can access narrow openings. And some snakes, they can even fly. They climb onto branches and jump off, curling their body to glide through the air. The first snake robot we developed was Anaconda. This was built as a proof of concept of a robotic fire hose. The question that was asked was, why should the firefighters need to drag the fire hose into the burning building? Why can't the fire hose climb in by itself in advance, carrying cameras and other sensors, providing information to the firefighters outside, such that they can plan and execute a safer and more efficient firefighting operation? Technologically, the idea was that the high-pressure water inside the hose could be employed both as a hydraulic medium for enabling the hose to move and as a fire extinguishing medium for the firefighting operation, and in addition as a cooling medium for cooling the robot in environments with extreme temperatures. The resulting robot, Anaconda, was 3 meters long, weighed 75 kilograms, had 20 joints, and it was the first water hydraulic snake robot in the world. And it received a lot of attention. But even though Anaconda demonstrated that the concept of a robotic fire hose was indeed realizable, it also demonstrated that there were a lot of research challenges to overcome when it came to controlling the robot, making it move forward and making it go where we wanted it to go. To look deeper into these research questions, we developed ICO, with electric motors instead of hydraulic, making the robot much lighter and easier to work with. We here see how it curls up against the obstacles, just as biological snakes do, and it uses the obstacles by pushing against them to move forward. For a robot to be autonomous, it needs to be able to sense its surrounding environment. And we equipped Kulko with contact force sensors mounted behind the spheres. With these, the robot can detect obstacles and autonomously push against them in an efficient manner to move forward. Wiko, on the other hand, does not need obstacles to push itself forward. It is equipped with passive wheels for the sole purpose of creating an anisotropic friction property. The reason why the robot needs this friction property we will get back to later, but we can notice here how undulations make Wiko move forward. We have already seen that one reason why snake robots are so interesting is their mobility. And this can, for instance, be useful for space exploration. And a feasibility study for the European Space Agency studied how the snake robot can be a helper for the rover, going into cluttered terrain and narrow openings where the rover cannot go. It is of particular interest to be able to go into caves because what's inside these caves has been protected from radiation. In addition to their mobility, the other reason why snake robots are so interesting is that the robot is a hyper-redundant robot manipulator arm, which can also transport itself. So we can equip it with a gripper or another tool in one or in both ends, and it can perform manipulation tasks, physically interacting with its environment. So space is one possible habitat for our snake robots. Me personally, I'm equally fascinated by our oceans. The oceans are tremendously important to us. They contain food sources like fish and seaweed. They contain minerals that we need, and a biodiversity which is crucial to maintain and which may, for instance, hold new cures to diseases. The oceans are also an important part of the Earth's total ecosystem and can provide us with important information about the state of the Earth, including climate changes. So the oceans play a key role in addressing our global challenges stemming from an increasing population and the corresponding need for energy, food and minerals, and for addressing the challenge of global warming. Yet, despite being so crucially important to us, we know more about the surface of the moon than of the bottom of our own oceans. Only a few percent of our oceans have been explored. So we need to get down there and explore to get more knowledge about what is happening and to utilize its vast resources in a sustainable manner, protecting biodiversity. But how do we get to the bottom of our oceans? Diving is one possibility, but this may be dangerous and it is very limited how deep divers can go. Ocean exploration therefore requires marine robots. We have three types of marine robots today. We have survey UVs, autonomous underwater vehicles, which are made for traveling long distances. They are torpedo-shaped to achieve good hydrodynamic properties, making them energy efficient. As you can see, they do not have manipulator arms, however, so they cannot interact with the environment, like picking up a sample from the ocean floor. If we want to interact with the environment, we use ROVs, remotely operated vehicles. These are vehicles equipped with manipulator arms. The box-shaped carrying vehicle is not as hydrodynamically efficient as the survey UV, so the ROV is better suited for short-range operations. In addition, the big box restricts access, and such an ROV is not able to access narrow spaces, like for instance between rocks or inside ice caves. To gain such access, the ROVs are typically made smaller and smaller, but as they are made smaller and smaller, the arms that they are able to carry with them also have to get smaller and smaller, and in the end we're left with a pure observation ROV, which may look something like this. So this robot gives access to narrow spaces, but it does not have intervention capabilities, no manipulator arms. So with the current marine robots, we need to choose between a robot that can travel long distances, a robot which can interact with its environment, or a robot which can gain access to narrow spaces. Since our goal is accessing and exploring the oceans, it can be smart to instead learn from nature. We here see how sea snakes move efficiently through water. Their body is long and slender, even more so than the survey UV, and in addition it is flexible, able to move efficiently through the water and in between rocks and corals. And inspired by nature, our research group has made robotic snakes that mimic these biological snakes. We here see the snake robot, which we named Mamba, moving around in water. It performs these simple undulations just like the sea snakes, and we see how efficiently it then moves through the water. Mamba is a demonstrator, a proof of concept, showing that swimming snake robots can indeed traverse the oceans. To fully understand snake robots, however, we do what we always do when we want to fully understand a physical system. We build a mathematical model of it. When we develop such a mathematical model, we use pencil and paper and write page after page after page until we finally understand how the snake robot behaves. And some people ask, why do you need a mathematical model when you have a physical snake robot like Mamba? And that is because Mamba is one particular snake robot, and everything we can observe from its behavior, the only thing we know for sure is that this holds for the member robot. This mathematical model, however, describes all the snake robots in the world, regardless of whether they are small or large, short or long, swimming or moving on land, and it shows us the structure and inherent features. So we use the mathematics as a language to understand snake robots, and by analyzing this mathematical model, we can find inherent properties of snake robots and biological snakes, and in this way we use mathematics to decode the secrets of nature. The first research question, the first thing we wanted to understand was, how do we make the snake robot move forward? We here see anaconda again. It moves using the same undulations that biological snakes use, but as you can see, it does not move forward. Using our mathematical model to analyze this problem, we could establish that the reason for this is its smooth surface. In order for undulations to make the snake robot move forward, the robot needs to have a certain friction property. It must be anisotropic, meaning that the friction in the sideways direction needs to be larger than the friction in the lengthwise direction. And biological snakes have this friction property due to their scaled skin. And in water, the hydrodynamic drag forces provide this property, also without these kind of scales, because of the long, slender body of the snake. So not only can we learn from nature in order to achieve mobility for our robots, but the robotics research can also help us understand nature and why it works like it does. So our analysis of the mathematical model tells us that in water, undulations will make our snake robots move forward, as Mamba demonstrates here. We can have different kinds of undulations. To the left we see lateral undulations, where the amplitude of the undulation is the same along the whole body. While to the right we see eel-like motion, where the head is quite still and the amplitude of the undulation increases toward the tail. Knowing then how to make our snake robots move forward, the next research question was how to make them move forward as fast as we would like. How would, for instance, the choice of amplitude affect the speed at which the snake robot moves forward? Would increasing the amplitude make the robot move faster, since it pushes away more water propelling it forward? Or would it make the robots move slower, as it has to move a longer distance from side to side in order to move forward? Again, the mathematical model provides the answer. It says that increasing the amplitude will make the robot move faster. In fact, doubling the amplitude not only doubles the forward speed, but the speed actually becomes 4 times as fast, and these experiments confirm this. Having understood how to make the robot move forward and with the speed that we want, our next research question was, how do we make the robot not only move forward but go exactly where we want it to go? In other words, how do we make the snake robot follow a given path? To achieve this, we use something called line of sight control. This is actually what most of us do when riding a bike or a car or any other vehicle where we do not have the opportunity to turn on any direct force in the sideways direction. We can only steer the heading and the forward speed. What we intuitively do then is that we look towards the path that we want to follow, and we head the bike or the car such that it is oriented towards a point that lies a certain distance ahead of us along this path. This distance is called the look-ahead distance and is shown in yellow here. As we approach the path, this point, since it is always a constant distance ahead of us, will also move forward, and heading towards this point will give a smooth and steady approach towards the path. Our mathematical model also tells us that this look-ahead distance needs to be chosen sufficiently large, or else the system becomes unstable. And you may already have observed this from inexperienced bikers or drivers who look just ahead of the bike or car, something which results in a wobbly, unstable behavior, while a good driver looks far ahead, uses a long look-ahead distance. In this experiment, we have told Mamba to follow this yellow path. We see how Mamba uses an undulatory motion to move forward, and it keeps a sufficiently large look-ahead distance such that it moves smoothly towards the yellow path. An additional challenge that the snake robot faces when moving in water is the ocean current. In this experiment, there is a current in the direction shown by the green arrows, pushing Mamba away from the path. And Mamba does not know which direction the current comes from or how strong it is, it only has position measurements. To cope with the currents, we use what we have called an integral line of sight algorithm. This notices that something is pushing the robot away from the desired path, and the algorithm autonomously adapts the swimming motion to compensate for this, and as we can see, the robot follows the path. So, learning from nature, we have found a robot which moves efficiently through water, with a slender and flexible body which makes it easy to access narrow spaces, like for instance between rocks, under ice, or inside shipwrecks. Snakes cannot stand still in water, however, they cannot hover. If the snake stops undulating, the ocean currents will make it drift away. And that led to our next research question, which was, why not combine the best from biology and nature with the best from technology? Combining the slender and flexible body of snakes with thrusters, giving the robot the ability to hover, for instance to inspect something or to pick something up. And we here see the resulting robot. This new marine robot combines several features of the existing marine robots into one tool. It has good hydrodynamic properties. It can go straight as a torpedo and turn by curving its body, and is thus well suited for long-range operations. It has better access capabilities than even the smallest observation ROVs, as it is slender and flexible, and this makes it able to go through narrow openings. And it can perform light intervention operations, turning valves and picking up objects, since the robot in itself is a manipulator arm. So in this way, we have moved from biology through university research, and in order to bring the snake robots out of our laboratories and into practical use, we have established a company called ILLUME. The name ILLUME is coined from the two words il, due to its biological inspiration, and illume, which means to shed light on and gain knowledge, which is exactly what we want to do underwater. And I will show a video illustrating the ILLUME concept.
Until now, subsea inspection and maintenance has relied on underwater vehicles with surface vessel support. ILLUME changes everything. It's a new type of underwater intervention vehicle. The snake-like body combined with underwater thrusters makes the ILLUME unique. Flexible and dexterous for complex manipulation. Straight like a torpedo for long-distance cruising. Slender and agile for precision hovering and maneuvering even in strong ocean currents. And operating in confined spaces no other vehicle could reach. Snaking around obstacles and through narrow openings, shifting into a U-shaped dual-arm configuration to tackle intricate tasks. Because the vehicle is modular, you can change combinations of joints, thrusters, and payloads. You can mount different types of equipment, like torque tools, grippers, and various maintenance tools. Cameras along the flexible body give the operator a clear all-round view during inspection and intervention. Best of all, the ILLUME is engineered to live permanently underwater, where it can safely operate 24/7, regardless of weather conditions. This means less use of costly surface vessels and greener and safer subsea operations. With the intervention AUV of the future, ILLUM is reshaping underwater operations.
The video showed the ILLUM concept with the very first ILLUM robot from 2016, which was tethered. Now we are on generation 3 of the ILLUM robot, which is untethered, can operate as deep as 500 meters, and which has higher autonomy capabilities. The ILLUM robot is a modular system, so it's like the Lego of subsea robotics, and you can create arbitrary combinations of modules. The third generation ILLUM vehicle has improved thrusters, which are more powerful and more robust, and the thruster configuration of the vehicle has also been improved. An important feature is active roll control, which makes the vehicle a lot more stable in the water. And the video data will be more stable, and sensors mounted along the vehicle body can be pointed in any direction by simply rolling the vehicle. In addition, the dual radial thrusters doubles the thrust in the sideways direction of the vehicle, which improves the ability of the vehicle to hover in strong ocean currents. Another improvement is that we exploit the length of the vehicle to achieve good video data. More specifically, we have installed strong LED lights at the head and the tail, and have installed an HD camera at the center module. We thereby achieve a large distance between the camera and the lights, which reduces backscatter and improves the video data. The joints along the vehicle can be used to steer the direction of the light cone from each end. And with the camera in the center module, the robot can record video of pipelines and the seabed during transit. The robot can also attain a vertical pose and then use its roll capability to scan 360 degrees and get a good overview of its environment. Pipe inspection is an important application for the ILLUM robot. In addition to moving along a pipe, just like a torpedo-shaped survey AUV, the ILLUM robot can also approach the pipe and wrap its body around it in order to inspect the pipe from multiple angles. The ILLUM robot is a general carrier device for sensors and tools. And to ensure a wide range of tasks and to make it easy to change the operational scope of the robot, the subsea docking station under development will include a payload rack with exchangeable tools and sensors. Each end of the robot will have an inductive interface for power and communication, which can be used either to charge the vehicle in the docking station or to connect the payloads in the payload rack. And with tools and sensors connected at each end, the vehicle becomes essentially a dual-arm robot. The two ends of the robot can collaborate to solve a common task. For instance, one end could grab hold of something to fixate the vehicle, while the other end carries out an intervention task, such as operating a valve. Or one end could provide a camera view from any angle towards a tooling operation carried out at the other end. Here we will see a video from one of the sea testings that NTNU has done with the ILLUM Snake robot. So the robot was delivered to NTNU, our home university, in June 2020. And we have a research vessel called Gunnerus, from which we perform sea tests. We see here how the robot can access really narrow locations, which would be really hard to get to with an ordinary ROV. And because, as I talked about, the positioning of the camera and the lights, we avoid backscatter. And here we see a video of ILLUM testing the navigation system in the Oslo fjord. The previous video was from the Trondheim fjord, so we use our fjords as testing sites. The robot here performs a mission plan, which is tracing an 8. And the tether we see, this is only to transmit real-time high-resolution video. The navigation is performed using an IMU and the Kongsberg Sunstone system. And here we also see the robot diving down, locating and inspecting a torpedo. The robot is able to move under and inside ice because of its slender and flexible body, and it can take samples since it can hover in water and use the tools at its ends to interact with the environment. The robot can also support aquaculture by inspecting the well-being of the fish and also the state of the nets, detecting and repairing holes to prevent fish from escaping. We have several man-made structures in our oceans, and it is important that these are inspected, maintained and repaired to pose as little disturbance to the ocean ecosystem as at all possible. The ILLUME robot is designed to live permanently at the seafloor, where it can safely operate 24/7 regardless of weather conditions. And since the robot is available at all time, any problems that should arise can be detected and repaired much earlier than today. So the resident robot gives both greener and safer subsea operations. One of the actors who are dedicated to this is Equinor, the Norwegian energy company. The ILLUME robots are now getting ready to move out to Equinor's Åsgard field, where they will work as subsea janitors. And I will end this presentation by showing a short video that Equinor has made illustrating how the ILLUME robots will work at the Åsgard field to achieve greener and safer subsea operations. So with this new bio-inspired marine robot, we are ready to explore the remaining 95% of our oceans. And the ILLUME robot will be a useful tool for both exploring the oceans and for the offshore energy sector in the times to come. And it all started with the curiosity-driven research, asking the question of how can we learn from nature to achieve high mobility for our autonomous robots. If you're interested in more details about this research, you may have a look at this review paper, which includes results on both terrestrial and swimming snake robots, and the Snake Robots book, which focuses on terrestrial robots. And you can also find a complete list of publications at my homepage. Finally, I want to acknowledge all the members of the Snake Robotics Research Group at NTNU, and also thank all co-authors from other groups for the great cooperation. Thank you, and thank you all for your attention.